Hello everyone and thanks for coming. My name is Jessica Palmer and I will be talking about using Python in TouchDesigner to make interactive experiments. I'm originally from Toronto, Canada, but I moved to Berlin about 2 years ago and I just can't seem to leave because of all of the brain science. I mostly work for Dr. Petra Ritter at Charité in the experimental neurology department. Our current project is a SDK and app project which uses neurofeedback and some brain visualizations. My background is in art and design, but slowly over the past 2 years I've become a developer. I'm not sure how it happened. And I have about 1 year's Python experience. My favorite tool is TouchDesigner. What is TouchDesigner? It's a real-time visual development platform for Windows. You mostly get around using Python, and you can use Python exclusively, but if you're into it, you can also use C++, and you can also use shader language to write directly to the GPU. It's super popular with VJs and projection mapping, but that's not the only use of TouchDesigner. There's people who are using TouchDesigner to combine data science and every other type of science and art to make interactive experiments and experiences. This is the work of Matthew Reagan, and he's a super favorite of mine. On the left is a clock, which is made out of the sampling of a video in a room over time. The outside rings represent long time durations, like months or years, and as you get towards the center, you get down to seconds and nanoseconds. The result is an image of a room over time, seen at once, as it's being created. The image on the right is a sampling of images pulled from different threads on 4chan. You might be able to guess from these colors what the most popular images are on 4chan, but don't think about it too much. The most well-known and most well-loved work done in TouchDesigner is the collaborative work between Amon Tobin and the V-Squared team. In this example, we have a 3D structure which is being mapped with animated video, which is being driven by data which is extracted from the computer that Amon Tobin is making his music on. I just want to point out here that this isn't a simple audio in, like a microphone, which is having like bandpass filters applied to it and the audio dynamics extracted afterwards. This is messages from his computer that represent the different instruments and the different layers of music and samples. These are being interpreted by the V-Squared team and turned into generative animations and video clips which are being triggered by different behavior of the music playing. So it creates a different experience every time. In this example, the images on the both left and right are taken from data from a Kinect using the depth sensor. On the left, the data is being turned into a 3D geometry, which is describing the form of the performer while she's moving. She's even taking a backstage to the animation. You can see her in shadow in the foreground, and her actual performance body is the image created from the data. On the second image, the same information from the depth sensor is being turned into a points cloud, which describes her motion over time in the space and also interacting with the bodies of other performers. Sometimes the Kinect even confuses them for the same person, which is interesting. I just want to point out that all of this is happening in real time with Python. This is like being calculated probably about 60 times a second. And I take this for granted because when I first started learning Python, I was also learning TouchDesigner at the same time. I just thought this is how you do. I didn't realize until later when I was watching my colleagues try to draw brain data traces in MATLAB that usually these things don't happen so quickly. I love TouchDesigner because it supports my workflow. It's fast and intuitive, and everything that I do I can see happen immediately, including the errors. Here's an example of just some normal Python script that I wrote. It's not important that you can't read it, but I just want to point out that this is a linear workflow from top to bottom reading instructions. It's not exactly how my brain works and how I'm thinking about when I think about projects. This is a little bit closer to how I think about building something, a network diagram. It's still not perfect. We have the inputs on one side, which are being organized by modules, which go into instructions, and then those get relayed to the different assets. And at the end, you see the final product. I'm going to show you a video of what it's like to work in TouchDesigner. I don't know what to call this exactly. Maybe I'll call it a real-time inception type network. It's a node and wire system. It's a hybrid of visual programming and text-based programming, and it's network diagrams all the way down. In this way, I can visually organize different behaviors and different assets and different modules in physical locations and move them around and reassemble them to create new machines. TouchDesigner is a complete environment. You have everything you need to make your project right away from start to finish. You make the prototype, you write the instructions, you do the experiments, and you run the experiment in TouchDesigner. It's easy to make scalable and reusable components, and it's ready to go with about 1 million inputs and outputs. You have access to real-time 3D graphics through Python alone, and the full power of your GPU. The workflow is however you want it. You don't have to make a crazy spaghetti network diagram like I made. You can keep it nice and neat and tidy, or just text if you like. You don't have to be a wizard to make very adequate things, but if you are a wizard, holy crap, you can already whip up something totally awesome with the Python that you already know. For me, it was like putting on a mech suit. Suddenly I had access to everything, and I could build what I wanted almost right away. So in the early times, someone in the lab asked me to make a simple experiment to expose subjects to a random sampling of audio clips. And she also wanted to record the brain data at the same time, and she also wanted to give the subject instructions in a particular sequence, which is automated. And she wanted to run this experiment over and over again about 50 times a day. We made this experiment together in an afternoon. Before I continue, I'm going to give a quick overview about how TouchDesigner works. It's a node and wire system. Nodes are called operators, or ops for short. And they have very cute names and colors which represent the type of data that each of them handle. Only operators of the same class can connect to each other with wires, so an image to an image or a video to a video. Actually, a video can go to an image, but a 3D object to a 3D object, a text object to a text object. But you can also convert them between each other. So for example, on the left, we have a gradient top or a normal texture being turned into a data channel with a chop, and then being converted again into a table of values. So the operator on the far end is a description of the original image with a row for each pixel in the image, and the different columns are the RGBA channels. This is a noise chop, which I'm going to use as an example, and it exists in the visual operating world with a parameters page attached, which you can start using right away to change how the noise works. But also every operator can be accessed with Python through different flags and different methods, etc. There's about 1 million. This is just an example where you use Python to grab all the data from this noise channel. The flags will change the behavior of this operator in the visual environment. So for example, you can tell this operator to be bypassed in the network. I'm not trying to sell TouchDesigner. I just want to get you excited about all the cool stuff you can make with it, and all the data that you can gather and visualize, and all the ways you can interact with data. But obviously, I really love TouchDesigner, and let me count the ways. So in this chart are a few examples of the inputs and outputs which are already available to you in the graphical environment. So you place one operator into the field, and you have access to all of the data on the Kinect camera, for example. You don't have to understand how the Kinect works. You don't have to read the Kinect documentation or understand the SDK. You can use the Python you already know to get information from the Kinect camera and start using it. Same goes for out. So you can out your project to any virtual reality, which is supported by OpenVR, including the Oculus Rift and the HTC Vive. It also has tools ready for you to communicate with your own custom devices too, for both in and out, and it's ready for particular systems like commercial lighting rigs and lasers. Just to show you how easy this is to work with different inputs, this is an example where I'm using 5 different inputs at the same time. All of these are supported by TouchDesigner right away. You can drag wires from one component to another to change the flow of the data, but in this case I'm going to use a switch and some buttons because it's more tidy. So this is just displaying normal keyboard activity. This is displaying the gyroscope on my phone, whether or not I'm shaking it, and I can use the touchscreen as a toggle. I've set it up so that every single one of these inputs can go into the same visualizer, which is just some simple text and particles. And also, I can move all of these components to a data saving module at the top if I want to record everything that happened. In this case, I'm using a MIDI controller called the OP1, and just to get which keys and which pots I'm using. In this case, I'm using the Muse, which is a commercial EEG headset, and I'm just printing out the alpha and beta, and if I relax enough, it will print out if I'm relaxed. It's really hard to relax. In this case, I'm using the Kinect camera and using the facial tracking to determine whether my face is being tracked at all and which face I'm making. I'm going to show you later the one line of code I used to make this happen. It's this. All you have to do is ask the Kinect for which facial expression and then do basically whatever you want. I'm really excited about this. The best part is that there's Python everywhere in TouchDesigner, so many different opportunities to use a lot or a little bit. So in this case, you can write Python directly into the parameters fields in the visual environment. So in this case, I'm using a module which returns how relaxed or focused a subject is to make a dancer move faster or slower based on this information. So I just took that thing and put it into the speed of a single video clip, which is one of these dancers in this scene. That's super fast. You can also write Python as normal in a data operator or in the terminal, and other operators or other scripts can execute these entirely, or in the case of mods, just call a particular function. Some operators have events, such as this timer, and it's quite handy because it already comes attached with this attached DAT with all the possible events of this timer. So, for example, the timer will know when it's done, when it's being reset, when it's ready, when it's finished, if it's looping, and you can just inject tiny bits of Python into that particular event to cause a particular thing to happen. You can also send data to TouchDesigner with Python using network sockets, and it comes into TouchDesigner all formatted and ready to use. So you can also send data out of TouchDesigner with OSC or UDP or TCP IP by just placing an operator and sending a message over that type of network is as easy as saying, this network operator dot send, and then your message. If you wanted, you can decide never to place an operator with a mouse ever. You can ignore the visual environment completely. All operators can be created or destroyed with Python alone. And on the chart over here, we have examples of some of the ways you can modify operators via Python. And you can also modify them at creation or after creation by addressing them by their operator name. So in this case, we have a piece of text which creates a sphere object called mySphere, and then in the second text object, we have something that destroys any object by the name of mySphere. There are also some Python modules automatically in TouchDesigner that are pretty handy. Store and fetch is interesting because it's a fast and easy way to store anything as a global variable, including an entire operator or an entire network of operators. You can also talk to operators by their name using me.digits or parent.digits. Parent.digit refers to that operator's place in the hierarchy, so operators above it and below it. So this is handy when you're using replication and you have an unknown amount of operators or a very large amount of operators with Python scripts attached to them, and you just want to know what the name is in order to perform a particular function on that operator. So say you have 100 noise channels and you want them to all be unique, you can make the seed of that noise equal to its me.digits. In TouchDesigner, you can use as much or as little Python as you want. It's equally possible to create a project entirely with Python as it is to create one without. You might be asking what you can do with this, and basically anything. You can hack some devices you have lying around, you can make a game, you can collect data en masse, you can prototype software. For me, working on the app and SDK right now, it's much easier for me to prototype something in a day in TouchDesigner than spend 2 weeks doing it in Xcode. If I want to find out if a game mechanic is fun or not, I can invest a little bit less time, improve it before I spend all that time building it. You can also turn your data skills into art, and you can design and execute complete science experiments, and you can make something that's a little bit of both. I'm now going to talk about a project I worked on with some brain scientists at Charité here in Berlin and Baycrest Home in Toronto. My virtual dream is both an art installation and a science experiment. My virtual dream is a collective neurofeedback experience where 4 subjects could control layers of video with their brain, and also music. I worked with a BCI team to make something that was simultaneously a collective interactive experience, but also a novel way to study the brain. Don't make noise. In my virtual dream, 4 subjects were fitted with commercial EEG headsets. We wanted to collect data to see if people learned how to control their brain state, either relax or focus, within the short time frame of 20 minutes. We also wanted to test and verify if neurofeedback could be used as a reliable input. Did the subjects feel in control of the dream? And how does the data compare here, gathered in the wild, as it does to data that we collect in the lab? You might recognize this from the first video. This is my control panel for my virtual dream. I can monitor the subjects and the progress of the software, and just in case something breaks, change the settings. In my case, this is the top layer of my network, and all the guts are underneath. The first challenge was getting the brain data from the headsets. The brain-computer interface team first acquired the data from the headsets and determined the state of the subjects, which was where they were on a scale of relaxation to focus. This was pre-processed and sent to me over network. I'm using a replicator here because I designed the software to include any number of subjects. We settled on 4 later, but we could change this in the future. Here I organize and define the data and what to do with the data. A player is defined by their score, their color, the video and music that they control. I can also define if they're on a team in the case of large volumes of players. In the past, we had up to 20, and we've discussed going up to 100. Players have momentary and a cumulative measure. Momentary is their immediate state at this moment, which fluctuates wildly. It's hard to control. Cumulative is a second measure, which is a description of their state in general. More points are awarded to cumulative, the more they maintain a relaxed or focused state. Both of these measures are used for the players to tell them about how they're doing and to give them constant feedback. When you zoom out of the network, it looks like this. I think of it as a machine because I can swap out parts at any time. I can make new components which change the entire behavior of the experiment, and I can take components from this experiment and make new experiments. It's organized by function and it's color-coded. There are different areas of the network for connections, player identity, how data is saved, how the audio and video assets are classified, and how different behaviors of the program work and interact with each other. The second challenge was graphics. I wanted to keep it modular and scalable. I wanted to be able to add more scenes and animations easily, and I wanted to be able to do the same for the music. I wanted everything to reflect the state of the player, and I wanted to control everything with Python scripts to make it automatic. Here's an example of a bank of dream images that were used to make the entire presentation. Each component contains all the animation layers and all the special behaviors of each scene. They're given an ID and a classification in tables so that I can easily refer to them anywhere in the project and grab a dream by its name or type. After all of that, I was able to write this script. This is the dream selection logic, and it's called every frame when I need a new dream. This happens maybe 2 or 4, or it's anywhere between 2 and 4 times for each set of subjects. First, I need to know the mood of the dreamers. This is an amalgamation of all the subject states, which is either relaxed, focused, or somewhere in between. Then a set is made of all possible dreams which fit into this category. After this, I subtract the dreams which have already been played, so I don't get repeats. And then I select a dream from random from that set, and add that to the dream set list, so that it doesn't get played again, and return the ID of that dream. Operators which handle dream scenes know them by their ID, so I can queue them with the script anywhere in the project. And when it all comes together like this, it feels like magic. The entire 20-minute experience for the 4 subjects is triggered by a series of daisy chain timers. Remember when I showed you the event handlers on the timer chop where you can put Python instructions? It's basically this a lot. I did this so that I could edit the length of the scenes from a single table to adjust how the whole experience played out. Maybe I wanted it much shorter, or maybe I wanted the intro to be really long so that someone could give a talk at the beginning, or maybe I just wanted it to run really quickly so I could debug it. After the dream is selected, it's cross-blended with the previous one, and here I made a custom crossfade component since I wanted something fancy. It then goes through a bunch of special effects processing, and then it gets outed to one video still at the end of the network, kind of funneling down. And this is all of this stuff is happening 60 times a second. Here's a snippet from one of the timers. When the timer is done, it will execute the next dream and trigger the crossfade. There's also a function called shriek, and shriek is a special function close to my heart. This leads to the third challenge. This is a science experiment, and we want to look at the data after. Raw data is being saved by the brain-computer interface team, but they want markers from me so that they can go through the data later and find out what the subjects were experiencing when the data was being saved. I also want to be able to look at the text logs so that I can read what happened and recreate dreams just from text. I also want to monitor the experience while it's happening. Shriek is an elegant solution, or my elegant solution. It does everything at the same time. I can send marks over network so that the BCI can log it on their computer, and it also saves the events to my computer, and possibly it could do other things at the same time. People wanted to change the marks all the time, so tables, again, was the easiest solution. On the left, we just have the index for every event that could happen during the experiment. And the second one is the human readable string that I wanted, and the last one is the mark that the BCI team wanted. A colleague, Carolina Stosio, has taken the data collected from MVD and started to interpret it. There's still a lot to work to be done, but in this graph, it depicts the subject's ability to use a single type metric, relaxation versus the absence of relaxation. And the purple depicts the subject's ability to use a dual type metric, which is relaxation versus focus, which are not mutually exclusive, which may explain why it's more difficult. There's still lots to learn, and it will probably never end, and I hope that this talk helped you imagine how you might use TouchDesigner to make your own experiments. A great place to learn more, and probably all you ever need to know, are the tutorials of Matthew Reagan. There's also lots of really great documentation and a place to start with TouchDesigner on their wiki. I can talk about this all day, every day, so if you have any questions, you can send me an email or find me on LinkedIn. Also, for Long Night of the Sciences, we're going to do a demonstration of MVD and our Brain Modes app, and Dr. Petra Ritter will be giving talks on the virtual brain, which is an open source full brain simulator. Thanks for listening, and enjoy the rest of the great talks at PyData.
Very much for this interesting talk, and now we have time for any questions. Okay, I'll start. Can you please talk about is it like open source, or how can you get the fancy software?
You can get it for free to use right away, but the resolution is capped, and it is missing like a few features, but you can basically do everything that I just showed you in the free version. I think the educational version costs around 300, which will allow you to use the software in events where you're accepting money payments. And then there's like a super fancy version, which costs about 2,000, that you can lock your network so that no one can see what you did in the case that you want to take what you did and sell it to like a museum or another laboratory or something, and you want to protect your IP. But basically, it's free for messing around.
What about the EEG headset? Is that something that everyone can just buy, or is that some super fancy medical equipment you only have at the
The headset that we're using is called the Muse by a company called Interaxin, and it's a 4-channel EEG with 2 grounding sensors in the front, so it's very minimal and crude, and this costs about 300 Canadian dollars, I think, which is basically pennies in euros, I think. But I think the most capable EEG headset available for commercial use is the Emotive Epoch, which is a 16-channel headset. And I believe just normal, this costs about 400 euros, but if you want to have like access to all the EEG, you have to fork out for the SDK, and it'll run you about 700. You can also make your own. I think it's called OpenBCI, and you can get instructions on how to make your own from scratch.
Okay, thank you very much for listening, and let's thank Jessica again. And yeah.